Welcome to Chemi at KPS, your go-to YouTube channel for mastering chemical engineering numericals. Here, I break down complex problems, explain the fundamental concept behind each solution, and guide you step by step so you not only get the answer but truly understand the logic and principle involved in it. If you want to strengthen your problem solving skills and build a solid foundation in chemical engineering, you are at the right place. So join me. We simplify the numericals and uncover the funda behind the solution. Today, we will discuss about steady state diffusion through stagnant. Steady-state diffusion is a fundamental concept in mass transfer that helps explaining how molecules move through a medium when conditions remains constant over time. This means that often after initial period the system reaches a condition where the amount of substance passing through each layer of the medium per unit time stay the same indefinitely. So every point along with the diffusion path receives and releases the same amount of substance per second. Now, you see this figure, okay? In this figure, the vertical axis shows the concentration and the horizontal axis represents the position across the diffusion path, okay? So the straight downward sloping line represents the concentration profile from higher concentration on the left side, that is your C1, to the lower concentration on the right side, that is C0. The color gradient is clearly visible to you. Okay, the left side color is your orange and right side color is yellow. So the color gradient emphasizes the constant concentration gradient over here, and the color concentration profile illustrates how the concentration decreases as we move from one end to other. The orange color changes to yellow. The concentration does not vary with time, only with the position over here. The rate of mass transfer, that is the flux, remains constant at every location with the diffusion path. Okay, so in this case, the calculation of the problem statement is grounded in Fick's first law of diffusion. So the concept is crucial in chemical engineering, especially mass transfer across a stagnant film where maintaining constant flux is important for the designing. Okay, so the important terms I have written over here at the bottom, that in steady state diffusion the concentration profile does not vary with time, only with the position. So del C by del T is equals to 0 over here. The rate of mass transfer, the flux remains constant at every location with the diffusion path. And steady state makes calculation easier because conditions does not change over here. So Fick's first law is applied over here. Okay. Now let's solve the question. What is the question that is given over here? Question is given, benzene is stored in a tank of diameter 10 meter and open at the top. The stagnant air film, that is 10 mm thick, is covering the surface liquid beyond which the benzene is absent. If the atmospheric temperature is 25 degrees centigrade and the corresponding vapor pressure is 150 mmHg, then estimate the rate loss of benzene. Here diffusivity of the benzene is given, that is 0.02 meter square per hour. And the total pressure is also mentioned over here, that is 1 atmospheric pressure. Okay, now let's see this one in pictorial view. Now you see benzene is present at the bottom of this vessel. Okay, the benzene is pure benzene, nothing is mixed. Since benzene is pure over here, the partial pressure that is mentioned in this question, that is 150 mmHg, is equals to the vapor pressure of that. Okay, Then above this liquid level, a 10 thick stagnant air film exists over here. Air is present and that is 10 completely stagnant. Okay, beyond which the concentration of the benzene is negligible. That's why the partial pressure of this benzene is equals to 0 at the open of this vessel, top of the vessel. Okay, now you see the diffusivity is given in 0.02 meter square per hour. Okay, so when we start solving this kind of problem, we should see that it looks very easy problem, but you will face problem while solving and while doing the your unit change, unit conversion. Okay, you see over here diameter of the tank is given in meter and the thickness of the film is given in Again, the diffusivity is given in meter square per hour and vapor pressure is also given in your mmHg. So every case is the concentration are not same. We have to change the concentration. We have to, not concentration. We have to convert the units over here. Okay. So when we convert this unit, we should take care of that because in this case we are going to use the gas constant R. Accordingly, we have to change it. Okay, suppose some people are solving the gate problems. So first of all, when we solve the gate problems, we should see that what is the value that is mentioned in the answer, what is the unit of the unit mentioned in the answer. Okay, based on that also you can think of to convert the units over here. Okay, so the key assumptions I have written over here, that air above the benzene is stagnant. Steady state diffusion reached over here. The benzene evaporated immediately and swept away from the vessel. That's why the partial pressure of the benzene at the top of this vessel is equals to 0. Okay. Now, the temperature, pressure and the film thickness are uniform. It is not changing throughout the diffusion process. So now the solution. This is the case of diffusion of A through a stagnant non-diffusing component B. Okay, this is the condition. If the condition over here is not stagnant non-diffusing B, then the problem could have been solved in a different way. Okay, so when we try to solve this kind of question, since this is a molecular diffusion, Fick's first law of diffusion will be applied and the integrated form of the Fick's first law of diffusion is presented over here, that is Na equals to dAb pt by ZRT ln pt minus Pa2 divided by pt minus Pa1. In this case, you know that already dAb is the diffusivity, pt means the total pressure, Z means the thickness of the film that is above the benzene surface, R is the gas constant, T is the temperature at which diffusion occurs, Pa1 and Pa2 are the partial pressure of the benzene at two different positions. Okay, so first of all, while solving the problem, we will write the data that is mentioned over here. The tank diameter is given 10 meter and thickness of the air film is 10 that is your Z. Over here we have to convert this value of Z to meter, so it is 0.01 meter. Again diffusivity DAV is given in 0.02 meter square per hour. We know the unit of the diffusivity, that is meter square per second. That's why we have converted to meter square per second, that is 0.02 divided by 3600 is equals to 5.556 into 10 to the power minus 6 meter square per second. Okay, the total pressure is given in atmosphere and we cannot do the calculation by taking the value 1 atmosphere. We have to convert the unit again. The unit conversion says that your 1 atmospheric pressure is equals to 1.013 into 10 to the power 5 Newton per meter square. Again, another value is given, the partial pressure of the benzene or the vapor pressure of the benzene over here 150 mmHg. We have to convert this unit again to Newton per meter square. We know that 1 mmHg is equals to 133.32 Newton per meter square. So 150 into 133.32 will give you the value of 19998.4 Newton per meter square, or we can write as a whole 0.2 into 10 to the power 5 Newton per meter square. Okay. Since the concentration of the benzene at the top of the vessel is negligible, so we can write the partial pressure of the benzene at the top of the vessel is 0. So Pa2 is equals to 0. Okay. And accordingly, we have to choose the value of the gas constant R, that is your 8.314 joule per mole degree Kelvin. And the temperature over here, we have to convert it into degree Kelvin, that we know 25 degree centigrade equals to 298 degree Kelvin. Now we have all the values over here. Okay. Now we can put the values in the equation and we can write the molar flux Na is equals to 0.02 into all the values we have to mention over here. Then finally we'll get the value Na equals to 4.996 into 10 to the power minus 6 kilomole per meter square second. This is one that we have determined what is the flux. But the question is asked to determine what is the rate of loss of the benzene through a particular area. Okay, so the loss we can determine over here, the total rate loss of benzene, that is area we have to calculate. Area is equals to pi r square, so we are getting 78.54 meters square, and the total rate that we know that in the previous class also I have mentioned over here that W equals to Na into A. So we have to multiply it and you will get the value 3.92 into 10 to the power minus 4 kilomole per second. Okay. So now I hope you understood today's problem and try to solve it in your copy, pen and paper, and try to calculate it on your own once or twice. Try to understand the fundamental behind it and which equation will be used if stagnant film is given over here. Okay. So now let me tell you another thing. What is that? While choosing the value of R, we are getting confused. Okay. So we have to memorize the value of R definitely. If pressure is given in atmosphere, it is required to use the value of the gas constant R that includes atmosphere in unit, which is approximately 0.0821 liter atmosphere per kilomole degree Kelvin. But in this question, whether liter is mentioned, it is not mentioned. That's why we have taken another one. Okay, another value. What is this? For energy calculation, when the pressure is given in pascals and volume in cubic meter, then the value of R can be used approximately 8.314 joule per mole degree Kelvin. So while solving the problems of mass transfer, you try to remember this value of R, because the value of R will not be mentioned in the questions. Whether you are attending the GATE or any PSU or any competitive examination, you need to understand, you need to remember the value of the R to solve this kind of question. I hope you understood today's lecture, and thank you for being with me. If you have any question, definitely you can write it in the comments. I will take care of the your comments. I'll try to include in the further slides. Thank you for being with me, and if you like this teaching, definitely I'll suggest like, share and subscribe to KME at KPS. Thank you so much.